In this video, we will talk about a couple real-world applications for our modern atomic theory, particularly focusing on things that deal with isotopes. We will finish the discussion with an introduction of the concept of the mole. In our previous discussion on isotopes, it was mentioned that most elements have a variety of different isotopes, and what differentiates the isotopes is the number of neutrons. And because neutrons have significant mass, this leads to a difference in mass for the different isotopes. We can use this fact to determine what compounds are made of using something called mass spectrometry. So the masses of atoms and the percent abundance of isotopes of elements are measured using mass spectrometry. This is a technique that separates particles according to their masses. The general setup is very similar to what you would see in the cathode ray experiment, except instead of having a beam of electrons, what we have is a beam of molecules. So you take your sample, you heat it up to vaporize it, get it into the gas phase, pass it through an electron beam which ionizes the particles. This is somewhat similar to the Millikan oil drop experiment. So your molecules now have a charge to them. You then pass them through electrically charged plates which make the molecules move in a very unified direction. Those plates have single slits in them that enables you to direct a beam of molecules in a very confined and ordered manner. The charged particles then pass through a high-powered magnet which bends the particles. This is similar to the cathode ray experiments in which putting a magnetic field near the beam of electrons caused them to bend, except this time you're bending the path of the molecules. By adjusting the strength of the magnet, you can cause the beam of charged molecules to strike at different locations along a detector. Based on where they are striking, you can determine how much they weighed. And by looking at the distribution of how things are striking, the amounts that are striking in different locations, or as you adjust the strength of the magnet, which is striking in the middle, you can determine what the relative isotope concentrations are in your sample. And from that, you can determine what the molecules are made out of. So let's say you're looking at something that has chlorine, for example. You would see these difference in masses from a chlorine sample. And just quickly, the way that mass spectrometers give their readouts is based on the intensity of the largest peak. So what this would say is that the sample that had the largest distribution, or the most amount of molecules striking at one particular spot, gets scaled to 100%, and then everything else gets scaled to a percentage of that. So in the case of the chlorine, as we had seen before, chlorine 35 is roughly 3/4 of the chlorine. So the value here, the 3/4 or 75%, would get scaled to 100, and the chlorine 37, which would make up the remaining 25%, would get scaled up to what would be the equivalent of about 33%. Okay, so your most abundant mass, or your most abundant sample hitting the detector, gets the 100%. Everything else gets scaled up based on that. So this is about 30% of the amount that you see for the chlorine 35. So based on that, you can tell what the relative abundance of your isotopes are. And if you know the naturally occurring abundance of various isotopes, you can work out the elements that make it up. So the way that we can figure out the percent composition from the data that comes out of a mass spectrometer is using sort of the following idea. The mass spectrometer uses relative intensities, not percent compositions, as we said before. So the highest intensity is set to 100%, and everything else is relative to that. So if you want to go back from the relative intensity to the percent mass composition, what you need to do is take the total intensity, which would be the sum of all your intensities, right? Add them all up, take the one that you're interested in and divide it by the total. So chlorine, for example, if this is 100% and this is 30%, you would have 130% or 133% or 1.33 repeating for your total intensity. If you take 100 divided by 1.33, or sorry, if you take 100 divided by 133.3 repeating, what you come out with for your percent composition is about 3/4 or 75%, which is what the natural abundance of chlorine would be. On the other hand, if you take 33.3 repeating percent and divide it by that same 133, your total intensity, you get back about 1/4 or 25%, right? And so you can go from your relative intensities to the actual percent composition using this sort of idea. Where we actually see this being played out is in a couple different locations. Mass spectrometers are widely used in the diagnostic industry. Mass spectrometry can be used to determine the chemical makeup of substance. It's often coupled with gas or liquid chromatography. This is essentially a way of sampling out more complicated mixtures so that we can look at them one component at a time. If you've ever gone through airport security and had them swab your backpack with a little cotton swab and then put it into an instrument that looks like this, then what you've had happen is your contents analyzed by a mass spectrometer for the presence of nitrates. Most explosive compounds have this nitrate, an NO2 component to it. So if you're looking in the mass spectrometer, you're looking for something that weighs the same as NO2 and has the same relative ratios of the various masses that you would expect from the different isotopes of the nitrogen and the oxygen. So the presence of a compound with NO2 in it is a fairly strong giveaway that you are working with some sort of an explosive. The problem with this, and what you will be asked if it turns out positive, is were you ever recently working on a farm or in an agricultural industry, because these nitrates are also used as fertilizers. Another one that you might have seen in some airports is this large contraption that you walk through and it blasts little bits of air all over your whole body. It then sucks up that air and runs it through a mass spectrometer, also looking for the presence of nitrates. Another place where mass spectrometers get used is in the Mars rover. So you have this unit, this SAM unit here, which has a mass spectrometer. One of the reasons why mass spectrometers are really helpful for use in something like the Mars rover is it doesn't require any chemical components to determine the makeup of compounds. You just can take your sample, heat it up to volatilize any compounds, and then you run those gas samples through your mass spectrometer to work out what the chemical composition is. So that's how the Mars rover looks to determine what's in the soil. Is it uses a mass spectrometer, and it can keep using the mass spectrometer without running out of any reagents, because the mass spectrometry works based on more of an electrical set of requirements as opposed to chemical analysis. The last thing that we're going to talk about for this particular chapter is the mole. So a mole, aside from being a furry burrowing animal, is, in terms of chemistry, a mole is kind of like a baker's dozen, right? So a dozen is 12 objects, or you could think about like a gross of apples being 144 apples. So we have a variety of words that are used to denote a particular number. Mole is just another example of this. So dozen means 12, gross means 144, mole means 6.02214 times 10 to the 23rd power. It's a lot larger than a dozen or a gross, but the concept is the exact same. When you say 1 dozen objects, like a dozen donuts, a dozen apples, you're talking about 12. When we're talking about a mole, we're talking about 6.02214 times 10 to the 23rd power things. You can have a mole of anything. You could have a mole of marbles, you could have a mole of grains of sand, though these would take up large quantities of space, somewhere akin to the entire surface area or the entire volume of the planet. So molecules and atoms themselves are incredibly small. 1 mole of water, for example, is roughly equal to about a tablespoon of water. It's about 18 milliliters. What the mole enables us to do is go from looking at things on the microscopic scale to the macroscopic, back and forth. When we're talking about water, things that you're interacting with every day, we're talking about it on the macroscopic scale, and so we would use the mole. Our mole is sort of the macroscopic number for atoms. If we're looking down at the atomic scale, we're going to use atoms or molecules. Right? So the mole represents our mathematical conversion from the microscopic to the macroscopic and back. The number is going to be referred to as Avogadro's number, which is 6.022 times 10 to the 23rd power. We can use this value here with 4 significant figures is sufficient for most of the calculations that we're going to be doing. You don't need to have it any more accurate than that. Because we're going to be using this a whole lot, you need to memorize this value. So the units on this would have moles on the bottom. This is objects per mole. So there are 6.022 times 10 to the 23rd objects per mole. It will be a very good idea if you memorize this value, although on any test or exam it will be given to you, but it helps to not have to look back and forth for this number. It's a very useful number to have memorized.